In this second part, we have a presentation by Professor Nicola Marzari from the UCSF on the Maximally functions. So, Nicola is the father of Maximally functions, so that's why we have him here, and thank you for joining us. So you have 1 hour, and then.
Thanks, Feliciano. Thank you all. Very happy to be here in Austin. First time after a Mardi Gras for the APS March meeting. It was a lot of fun. So here we are going to do half an hour of introduction to, let's say, the theory of maximally localized Wannier function. And I'll show some applications, maybe different from what you'll see in the EPW applications, just to give you a little bit of perspective. Let me also start with 2 slides of a historical introduction to show how things happen in science out of the overall context of research. So this work is from 1997, so we started it in 1996. And what was happening during those years were 2 things. One is that there was a lot of excitement in the electronic structure community about what are called the linear scaling methods. So, if you think, density functional theory is a theory from the 60s, but it's only in the late 70s that the plane wave pseudopotential total energy method started to become feasible and known. It was the group of Marvin Cohen in Berkeley that really pushed that, and the phase diagram and the potential energy surface of silicon and germanium in all the different phases is what convinced the community that this was powerful and LDA was accurate. Early 80s, there were pseudopotentials for all the periodic table. Mid 80s, Carparinello molecular dynamics was developed. Density functional perturbation theory was developed in 1987. So the sky was the limit, I would say, at the end of the 80s, early 90s. And one of the ideas that got people very excited was the idea of escaping this orthogonalization bottleneck. Large-scale calculations are expensive because you have to keep every orbital orthogonal with every other orbital, and that scales as the cube of the size of the system. And actually, there were some early papers, I don't have them here, but just the year before, both from Giulia Galli and Michele Parinello in Zurich, and from Paolo Giannozzi and Stefano Baroni in Trieste, that were really pushing the ideas of looking for algorithms that would be quadratic scaling in the case of Galli and Parinello, or linear scaling in the case of Giannozzi and Baroni. And so there was a famous session in 1993 at the Seattle APS that was, overflowing with people sort of, discussing this possibility of doing linear scaling calculations, and so really expand the length scales of the problem that one can do. So this was one of the driving force. And again, the concept in all linear scaling approaches has to do with locality of the electronic structure, and in particular, most often, with localization of the orbitals, because if 2 orbitals are far apart, you don't have to orthogonalize them with each other. So localization starts, coming into the frame of mind of the condensed matter physicist. It had been already there in the quantum chemistry community from the 60s. People like Boyce or Rudenberg had worked at localization idea for molecules, but for solid, it was just much more complicated because, and I'll discuss it later, we didn't know how to calculate actually the position operator for a Bloch wave function that is completely delocalized in space. And we'll go into this. But the second element after the linear scaling that was very important was the development in 92, 93 of what these days we call the modern theory of polarization, understanding that polarization is really a Berry phase, an integral of a Berry connection, but that led also to the definition, the mathematically correct definition of a position operator. So if you know what is the position operator and all the powers of the position operator, you can understand also if and how things are localized. So this was the conceptual starting points. So in some ways, it was just a matter of having, if you want, the right idea at this time, and working through the math that was a little bit complex, to say the least. Now, this you all know, but just again to set a language or to remind everyone, you know, if we have a periodic Hamiltonian, it commutes with all the possible lattice translation. I will use a capital R for a Bravais lattice translation. And so Bloch's theorem tells us that we can choose as common eigenstates. We don't have to, but you know, we can choose common eigenstates to the Hamiltonian and all the possible translation operator eigenstates that have this form. So they are labeled with two quantum number, an integer quantum number n, that is what we call the band index, and a continuous quantum number k that we call the quasi-momentum, and where k can be limited to live in the first Blount zone. So these are the two quantum numbers, exactly as in an atom we have n, l, m, the spin. I'm not discussing spins here, but so we have two, but k is continuous, so we have many more states. And the form, and that's very important, of these eigenstates of the Hamiltonian, so that they can be labeled with these two quantum numbers, is given by a periodic function, u and k, modulated by a phase. You see k lives in the first Blount zone, so this is a periodic function with a wavelength that is larger than the primitive cell of the crystal. Okay, I want to prove Bloch's theorem for you. You can see it saying the Ashcroft-Mermin. But what does it mean in practice? Well, you know, if we want to look at the eigenvalues of all the states in a crystal, you know, we label them with the band index. Here we have just one band, n equal to 1, but k lives everywhere in the first Blount zone, in this case of this one-dimensional crystal. So every point on this continuous red line is an admissible eigenvalue for our system. The eigenstate psi will be given by a periodic part, u and k, modulated by e to the I k dot r. So if k is equal to 0, there is no modulation, and our psi eigenstate is periodic. If k is different from 0, there is, you see, this long wavelength modulation. In practice, it has a real and imaginary part, but you can see it clearly. Of course, you know, the periodic part is not going to be the same. Here it looks a bit like it's the same. It's just because we can't draw maybe two fancy things. But you know, the uk will change as a function of k, and the modulation will change. But the eigenstates are delocalized, and themselves, you see, they are not periodic. Okay. Now, the question that Wannier posed himself, Wannier was a Swiss physicist that moved to the US, and he looked, you know, at a different representation that had a number of interesting properties that I'll discuss in a moment, and we call it the Wannier representation. And it's basically a Fourier transform. He says, well, let's, you know, keep the band index n. So we take a band, maybe this could be, you know, the bottom valence band of gallium arsenide, and we transform it. You see, we perform this integral on the Blount zone of our eigenstate times this phase factor e to the minus I k. That's the, you know, quantity that we are integrating. So it's going to disappear in the resulting transformed state. Dot, this is not anymore a phase. This is not a lowercase r. It's not a function that depends on space, but it's a Bravais lattice vector. Okay, so this is what Wannier said. We could have this transformation, and then you know, we'll see the properties again. This Rn have interesting properties that, you know, if you change, maybe that's the most important, r capital R into r prime. The new Wannier function is actually just a periodic translation of the previous one. But there is a problem with this definition, that is the Schrödinger equation doesn't fix the phase of psi. You calculate with different codes and maybe the same ingredients, the same pseudopotentials, your psi, you will get a random phase because there is nothing that establishes what that phase is. And so if you want, in reality, what we are doing when we are doing this Wannier transformation is that there is we call it a gauge freedom. There is an arbitrary phase that is for every eigenstate psi, that is for every band n, for every k point k, there is an arbitrary phase that can be added to this transformation, and this in square parentheses is still a very valid eigenstate. And there is one thing to think at, that is when you do this Fourier transform, what is important in the theory of Fourier transforms is that this object needs to be smooth, let's say just generically, not in a mathematical sense. There are mathematical statements, but it needs to be smooth as a function of k. If, as a function of k, this object varies discontinuously, this is going to induce a long-range decay, or in the limit of what happens in an electronic structure calculation, where at every k the phase is random, this object is not localized at all. So if you want, Wannier functions were a nice intellectual construct, but no one built them in practice. First, because we really didn't have, except in tight binding, sort of electronic structure model of this psi and k, but this problem of gauge freedom was not fixed. And the idea of localization is a bit more complex to analyze, but here I have really a sort of very hand-waving hint that Wannier functions should be localized. And in particular, we are going to look at a Wannier function. You see that is the transform for, let's say, the home cell. So when the lattice vector capital R is equal to 0, so there is not anymore that phase factor in there, that e to the ik dot capital R. And we are going to look at this Wannier function, in particular, what are its values, apologies, for not points in space in general, but points that corresponds to lattice vector Ri that are farther and farther away from the R equals 0 for which we have built this Wannier function. And you see what happens is that if we evaluate this expression, for the home sitting Wannier function, not a generic R, but in the particular case for R being a Bravais lattice vector, this capital Ri, what we have this integral, and now, what we have here, because this R that we are evaluating is a lattice vector, so it's always the same value. So this is a number, and what happens, again, it's really hand waving, but as R becomes larger and larger, basically you are integrating a function that oscillates very wildly, and you can take the sort of suggestion that as R becomes really large, this W0 goes to 0. So these Wannier functions are built with the goal of being localized in space, provided, again, the UK or psi k is smooth. There are many sort of more subtle mathematical demonstration of this localization. Gianluca Panatti at the University of Rome has done a lot of work on this in recent years. So I discussed the phase, but in reality, we wanted to play around a bit more with these bands. And, recall that, say, in our total energy functional, in density functional theory, in Archie-Fock, in all these singles, later determinant theories, what we have is that the total energy and the charge density is invariant for transformation between all the bands. So if you have a molecule a unitary transformation between all the orbitals in a molecule, or if you have a solid, for unitary transformation for all states at a given k point. So if you want, we have a more general, say, gauge freedom. That is, for every k point, it's not only a matter of fixing the smooth phase of the wave function, but we can actually mix different states, different bands at the same k point with a unitary matrix, number of bands times number of bands, unitary matrix. So if you want our most general freedom in our Wannier transformation was building Wannier functions Rn that comes from this double unitary transformation. That is, at every k point, we mix around all bands. Suppose that we have, again, gallium arsenide. So at every k point k, we can mix around these 4 bands. And then we perform this integral. And if you think of this integral as, again, discretized on a mesh of k points, that's, again, another unitary transformation. So it's a double unitary transformation. And what are the degrees of freedom? Are these matrices. Psi and k are given us by our electronic structure code, whatever electronic structure code you use, with all the randomness in the individual phases that the code throws at you. And then you take this, maybe gallium arsenide, 4 states at every k point. You want to mix them all together. This unitary matrix includes, obviously, also the choice of all the phases that you want. And the idea was to, make something useful out of this results, out of this Wannier functions. So this is, again, looking at the general Wannier transformation and looking at the properties that are built in this double transformation. That is, because it's a double unitary transformation, the Wannier function Rn span exactly the same Hilbert space as the psi and k. But what happens is that they are all translational images of each other. So instead of capital R, you put a capital R prime. That Wannier function is just going to be this previous one, but translated by the difference between R and R prime, and they are orthogonal with each other. But out of this, they could still be messy. They could be, very complicated. They could have no physical meaning at all, because here we can just put whatever we want in this unitary matrix. We can put just, diagonal identity matrices, and it's whatever the code gives us. And if you were to do that, you would get something that is just a garbled mix-up of states that doesn't mean anything. So how to make progress? That is, how could we choose this n bands times n bands unitary matrix so that these Wannier functions start to make some sense? And in particular, we wanted these to be localized. There is a heuristic way to do this. Actually, sorry, I've forgotten this slide. With this sort of formalism, we have also the possibility of choosing, say, of transforming maybe just in this case the bottom band of gallium arsenide. We could mix together the top 3 valence bands. We could mix together all the 4 valence bands. So that is, we are going to mix together what we call composite set of bands. That is, group of bands that might be sort of mixed up between each other, but are separated, you see, by gaps in energy below and above. So how to choose these matrices to make sense? A very simple possibility is doing this. That is, taking a localized orbital, Gn, that somehow represent what we would aim the Wannier functions to be, and transform the psi mk into this phi and k using this scalar product between the localized orbital and the Bloch eigenstates. Now, this, of course, is not a unitary matrix, but there are a simple procedure to make this unitary, so it's not really a problem. And the beauty of this procedure, you see, is that it becomes indifferent to any mixing that you could do between the psi. You put a phase in front of the psi, you put it in front of the brother, will be a counter phase in front of the ket, it cancels out. You put a matrix, unitary matrix, it will cancel out between the bra and the ket. So these phi are now completely independent from any phase factor or from any arbitrary unitary rotation that you could do between your Bloch eigenstates. So you have removed this gauge freedom, and what you obtain is really driven by your choice of G. So you can make this psi G unitary with a loading orthogonalization, and you're good to go. This is still a sort of heuristic. The result will depend on your choice. So it was done, it was used, but we didn't like it particularly. And instead, what we did is, well, let's establish a formal criterion of localization that probably doesn't take Albert Einstein to figure out. And what we said is that we want to choose those gauge freedoms, to choose those unitary matrices U, so that the Wannier functions that we transform, okay, suppose we have gallium arsenide, we have 4 bands, and in the Bloch representation, we would have 4 bands at every k in the Brillouin zone. Instead, in the Wannier representation, we have 4 Wannier functions in the home unit cell that we call 0, and periodically translated in every other unit cell. So if you want the complexity, the computational or numerical complexity of the problem is the same. You have a k that is, if you want, continuous, but is actually going to be numerable, and you have the same numerable countable infinity of Wannier function in all the different cells. So because in every cell they are the same, we just define the localization functional as being the sum of the Wannier function in one of the unit cell, in this case in the home unit cell 0, and the localization functional is nothing else than the spread around the center. So you see we are calculating the expectation values, if you want, of R minus expectation values of R, and so the usual math would give you the expectation value of R square minus the square of the expectation value of R. So this is the localization criterion. It has no physics built in it. There are other localization criterion that one could make up. We could have used R to the 4th, say, why not? What the chemists did in the 1960s were using other localization criteria like the Edmiston-Rudeberg criterion that said that we want to maximize the Coulombic self-interaction of the orbital with itself. Broadly speaking, most of these localization criteria give you very similar results. So there is, no theorem, no physics that this is good, and it's by no means unique, and it has no particular value. It's very simple. It has some nice mathematical properties that I describe in a moment, but one could have used others. They always look the same. If you start looking at molecules, every now and then you find special cases that the chemists were very upset in the 1960s, that if you looked at CO2 and you use this localization criterion that goes in the chemistry literature under the name of Foster-Boyes, CO2 looked like having actually triple bonds between the carbon and the oxygens. And they sort of liked more the Edmiston-Rudeberg criteria to give rise to what was more the chemical intuition. Anyhow, we chose this, and so our goal really is now to do this Wannier transformation where the U's are the unknown, and we take the psi from any electronic structure code that we want. We perform this double unitary transformation, but we actually choose the U, and you'll see it in a moment. It will be an iterative refinement of the U. to make the Wannier function, the resulting Wannier function Rn, as localized as possible, and so to get something that somehow satisfy our sort of chemical understanding of bonds in solids. So if you were to do, say, crystalline silicon, you would get a Wannier function that would look like the one on the left, a bit more perfect than this one that is taken from amorphous silicon. And if you were to do amorphous silicon in regions where the coordination is messed up, you would get something else that looks different and is going, at this stage to tell us something about the chemistry. Actually, at the beginning, and I'll come later, the application, we were originally thinking that, this may be as a tool in addition to linear scaling to understand the chemistry of materials. Now, there is one nice thing that comes out from this definition of the localization functional that you can see if you basically add and subtract the off-diagonal terms. You see, if we add and subtract these terms with the Rm quantum numbers. And so omega can just be rewritten as the sum of two more complex quantities, if you want, omega I, that's how we called it, and omega tilde. But, things actually become simpler. They look more complicated, but they become simpler because it turns out that both quantities are positive definite. It's very easy to understand why omega tilde is positive definite, is a sum of square. Omega I requires a very brief demonstration that I'll do in the next slide. But the other beautiful thing about omega I stands for invariant, is that omega I is gauge invariant, is oblivious of whatever set of n bands times n bands U matrices you choose at every k point. You can do whatever you want. Omega I will never change. Omega I is invariant. So, there is like a hardcore part of the spread of the Wannier function that you will never manage to go below it. I mean, if you're lucky, you can get omega tilde to be 0, and in general, in 3 dimensions, you cannot, but omega I will never go to 0. Now, how to demonstrate that omega I is positive definite and is gauge invariant? This is, just using the projection operators. P is the projection operator over the occupied states. Q is the complement in the Hilbert space. This is something that is used very much in density functional perturbation theory. It's used very much in calculating exciting states without explicit sums over the empty states. But if you rewrite omega I, and I won't go through this, you have it on the slides, in terms of this projection operator, so you see the last expression is really a sum over the Wannier function in the cell of an object that is really positive definite, because it's sum of the square, and because it's defined exclusively through the projection operator. The projection operators are invariant for all the gauge transformation. You put a U dagger in the middle of this, and it cancels out. So this object is gauge invariant. So we're almost there. So the last issue is actually calculating this localization functional, and calculating the localization function has this complexity that has to do with the fact that the expectation values of the position operator are ill-defined in a periodic system. You see it right away. If you have a UK, this is actually for k equal to 0, so it's fully periodic, and you want to calculate what is the expectation value of this position operator on this UK in the domain of definition, you understand very well that this quantity diverges or is ill-defined. Now, Blount in 1962 sorted it all out. He had, developed basically the modern theory of polarization and the understanding of the position operator as an integral of a Berry connection, but somehow, it wasn't used or it wasn't realized, the connection. But basically, he noted that while this integrals in real space are ill-defined, you can perform this transformation using this so-called Blount identities. Again, it's a very brief demonstration here. The very interesting issue is that the quantity on the right, this integral of the expectation value in reciprocal space of the gradient with respect to the Bloch quasi-momentum with respect to K is well defined. So by using the Blount identity, you can calculate the position of a Wannier function of a real space ill-defined integral. And this is also what is used in the Berry phase theory of polarization. So this is the end, basically. So we need to calculate there are equivalent Blount identities for the higher order. So the expectation values of R square is related to the Laplacian with respect to K, R cubed to the third derivatives, and so on. So basically, if we wanted to calculate the localization of the Wannier functions, the term on the left, we didn't have to do it in real space. We could do it as this Benzene integral in reciprocal space, same for R square, and we just needed to calculate this gradient. And these gradients, this UK, gradient K, UK, we did it with finite differences. So this is a bit boring. I won't go into the detail, but basically at every K point, we can calculate the gradient by looking at the nearby K points and taking the appropriate finite differences, exactly as, if you have to take the derivative of a function, you look at a function not at your point K, but, K plus a small delta in one dimension, K plus minus another small delta, and you take the difference. So these B vectors now are doing this math in 3 dimensions, putting to all the neighbors. And so we built up a very simple, say, finite difference scheme to calculate this object. So now we have the gradient, we have the position operator, we have the second derivatives, we have the square, and at the end, the ingredients that come into the finite differences for the gradient, you see this expression here, is by finite difference calculating a matrix element between the periodic part of the Bloch orbital at certain K point and that nearby K point. So the ingredients are just these matrices M. So at every K point K, you calculate the scalar product between the K and all its, say, nearest neighbors indexed by these small B vectors and between all the bands. And you can then express the position operator, the square, everything that you need as a function of these matrices M. And you see, what is interesting is that this scalar product, could be done by a code with non-conserving pseudopotential and plane waves, a code with ultra-soft or PAW and pseudopotential. It could be done with an all-electron code, but we don't need to know how this has been calculated to calculate the localization functional and then to find out what are the optimal matrices to give us the most localized representation. So, your code of choice, Abinit, Quantum Espresso, VASP, Siesta, Fleur, Exciting, Castep, you name it, is going to be in charge of doing this. And the Wannier code can forget about the representation, the basis set, the plane waves, the local orbitals that are used in certain codes, and it just deals, and the only thing that it needs are these matrices, and then it does its algebra. It calculated all the, say, expectation values that it needs, and in particular, it calculates the derivative of the localization functional with respect to an infinitesimal rotation of the Bloch orbitals, because remember, we want to iteratively update these U matrices, maybe starting just from an identity, and change them and localize the Wannier functions until we have reached the minimum of that localization function. So to do that, you need to build a variational procedure a steepest descent, a conjugate gradient procedure in the space of unitary matrices, and you know, infinitesimal change is just a anti-Hermitian matrix. So I won't bore you again with the math. It's a bit complicated, but you know, it's somehow buried inside the Wannier code. And everyone, starting from me and probably David as well, has forgotten actually what is in there, so it's lost. But you know, what you need is really this gradient, the derivative of the localization functional with respect to an infinitesimal unitary transformation, and then you just keep going down in the direction of the gradient. What we do is with a conjugate gradient minimization. So at this point, you have everything in place. You can take a system, say you can take, in this case, silicon, and you calculate silicon with your electronic structure code, you feed it to the Wannier code, it does the minimization of the localization functional, and what you get, say for silicon, are 4 objects in each unit cell that look very satisfactorily as a covalent bond. You do gallium arsenide, they also look like the exact same covalent bond, but somehow polarized towards the arsenic. As I showed you before, you do amorphous silicon. Most of the time, it looks like a covalent bond slightly deformed, but every now and then, you find out that, you know, locally, the electronic structure looks a little bit like different, and that's actually very precious to understand the electronic properties of the object. The math that I, you know, described remains valid if instead of having a solid in periodic boundary condition, you have a molecule described with periodic boundary condition in a unit cell that is large enough so that it doesn't interact with its images. Now, the chemists didn't work with periodic boundary condition, implemented these localization approaches in the 1960s, so they could localize, say, the molecular orbital of benzene, exactly as you see. This is Foster-Boyce localization. You see a hydrogen-carbon covalent bond, you see a carbon-carbon covalent bond, and you see the famous banana bonds of the pi bonding. And again, there is, you know, the Kekulé degeneracy here between 2 choices rotated by 60 degrees. And I won't go into the proof, but, you know, if you were to do with this math a molecule in a supercell and in periodic boundary condition, you would get exactly what the chemists get in open boundary conditions. So this is the end of the story for, you know, the construction of maximally localized Wannier functions. What to do with them? You know, there are a lot of things. You'll see a lot of use of these Wannier functions in this school. We have written this review of modern physics in 2012 that highlights many of the properties. You know, this analysis of chemical bonding is what came sort of in our mind first, but already then there was you know, a very strong connection with the polarization of solids. At the time, there wasn't a modern theory of orbital magnetization that came out around 2005. Both David Vanderbilt and Raffaele Resta on one side, but also here at UT Austin, Qian Niu developed, you know, basically the same idea. You see how, you know, in different places, you know, all of a sudden science is mature. And so magnetization also described in terms of Berry phases. You'll see a lot of work related to Wannier interpolation. This is what is used in APW. And maybe I'll tell you something a little bit about Wannier function as a basis and their use in different contexts, just to broaden the perspective. The thing that has also really exploded, and somehow maybe we could have forecast better, is really the relevance in understanding topological properties of solids that, you know, somehow started really in terms of calculation in 2009. So Chen Zhang actually used, and they acknowledge as what we had built to describe transport in solid state system in the sort of lead conductor lead geometry, where we used surface Green's function and iterative techniques. You use that to build the electronic states of topological insulators and show the metallic surface states. And from then on, a lot of efforts also driven by a number of people working in the field, and in particular David Vanderbilt, connecting the topological properties of a material with the characteristics of the Wannier centers of something that are called, I won't go into that, the hybrid or hermaphrodite Wannier functions. So very quickly, I told you already, one could look at chemical properties, and now localized Wannier function act as the best classical analog of quantum electrons, because you could identify the centers of charge as the position of a classical negative charge. And so it becomes very interesting to do, especially in disordered systems, not only the, say, pair correlation function of nuclei, but the pair correlation function of electrons and nuclei. And there is actually a lot of work that could still be done there, because they're really insightful in telling you when a state that from the geometric point of view looks quite boring is actually very interesting from the electronic point of view. These are two of the early examples from the group of Michele Parinello, amorphous silicon and liquid water. The other sort of piece of work that we did earlier on was to try and build a localized representation of the electronic states, not for composite group of bands, for say the valence bands of silicon, but to do that for system, let's simplify, for metallic system, where there is no gap separating the different manifold. And the idea was, let's look at something like copper. One wanted to identify the localized, the orbitals of copper, maybe also localized this, parabolic band, but it's really a periodic wide dispersion S band, and so on and so forth. And so we wanted to, basically deal with these systems, and we say we wanted to disentangle, we wanted to extract from this spaghetti here manifolds like this. Now, this is an impossible task in general, no? Take copper, and suppose you want to find Wannier functions that represent the D states. So you need a manifold that has dimensionality 5 that you want to localize. But if you look at the spaghetti here, there are regions in the Brillouin zone where you have only 5 states around here, but there are other regions where you have 6 states all mixed together. And so something has gotten to give. That is, when you do this operation of disentanglement, of extracting from the spaghetti the chemistry and the physics that you want, it's never going to be exact. You're always going to do, through your, say, criterion of disentanglement, something that needs to make the hard choices in the regions where there are more states than you want, say 6 states when you want 5. So what was our disentanglement criterion was something that came from the siesta community, and that was called, I think, the spillage. That is, what we wanted is to create a manifold, in this case of 5 states, that would be as much similar to itself as we move across the Brillouin zone. So the integral of the spillage, how much this 5-dimensional manifold changes across the Brillouin zone, should be as small as possible. So if you want the manifold dispersion, how the space described by these 5 states changes as we run around, should be as little as possible. Okay, so we extract things that globally look as similar as possible to each other. How to do that? Again, maybe I don't go into the details, but indeed it had to do to, now working not anymore with unitary matrices, but with rectangular matrices, because, we might change, we might choose all the states in this energy window. Sometimes we have 6, sometimes we have 7, we might have 8. So we decide what we want to extract. So at the beginning, we said, let's choose an energy window. maybe, it has up to 8 states, sometimes 7, sometimes 6, sometimes 5. I don't think 5 here. But it's one dimension of a matrix, and then the target is 5. So we now need to find the rectangular matrices that mix 8 into 5, or 7 into 5, or 6 into 5, such that these 5, as we surf around, are as smooth as possible. And it's actually very simple at the end. Even I could do it. And, it's just a matter of, again, optimizing, if you want, these projectors onto our target subspace as we move around. And the net result is that now we have the capability not only to take, say, this is silicon again, these 4 bands here, and localize them and get this very nice, let's say, bonding orbital. But we could do something a little bit looser. That is, we could say, let's take an energy window that goes from the bottom of the conduction up to something that it's up to us to decide. I'll comment later on how you could do this better. But let's choose an energy windows. Let's choose a target of 4, and let's disentangle, the subspace that is as much similar to itself as we surf of dimensionality 4 from the states in this window. Once we have disentangled that subspace, we localize it, and again we look at something that is very satisfactory, is an antibonding orbital. Or we could put everything together and let's say, let's take this larger energy window, let's have a target of 8 states, and we disentangle and we localize, and we get 8 now sp3 orbitals centered on each silicon, 4 of them. So you see, we had the capability to do whatever we wanted. Let's again go back to disentangling copper. We could disentangle out of this smaller energy window, or we could disentangle out of this larger energy window. And again, you see what we obtain depending on what we choose to include and mix together is different. Getting more states give us, a smoother subspace that gives rise to more localized orbital, but is less physical, okay? Because we have mixed maybe at this L point states like here that mathematically help us to make it smoother, but it actually means that when we diagonalize the Hamiltonian in that subspace, we don't reproduce the original bands. So you see there is a trade-off between, what you choose to mix and how smooth it becomes. The more you mix, the smoother it becomes. At a certain point, it would be perfectly flat, but you lose the physical interpretation. And again, you see there are this region of the Blount zone where you just can't win. You have to sort of, close down, cut between these different bands because you have 6 mixed together and you have a target of 5. So you can't reproduce the entire state. So in all this disentanglement procedure, there is an heuristic approach. Of course, you could make it better and reproduce perfectly things, not if you had, say, only 5 orbitals, but you could decide to have 9 orbitals. That is to represent not only the 4D states, but also the S and the P states. And then you could actually do perfectly everything below the Fermi energy. So it's really up to you if you want to construct exact representation of the occupied band structure up to energies above the Fermi energies. I'll show it later. Or if you want to have minimal models for maybe correlated electrons. One could try to get these green Wannier functions that do these parabolic bands. You could, play around. You could do a Wannier function that represent perfectly the bottom of the valence, and then in between is just interpolating. So it's really up to you. Now, this concludes maybe all this broad introduction to the, let's say, theory, or if you want, I should say the algorithmic of Wannier function. One nice thing that we did earlier on when I was still in the States, but with Alfonso Balderezzi and Michel Posternak at EPFL and Sandro Messid at the University of Cagliari, was indeed interface the Wannier code that I had written with an all-electron code. You see FLAPW code. This was a code that Michel Postenek has been developed coming from the Art Freeman group at Northwestern. And that's when we really, started thinking at, building the Wannier code as being able to interface with any electronic structure code in general. That has been, I think, a very nice thing, because it has allowed to have all these electronic structure codes that have been built by the community to interface with the Wannier code, and we say we have built almost an ecosystem. Now we have 10 minutes left, so let me quickly show some of the examples that are dear to me in terms of applications of this Wannier function. One that we started very early on was really using this Wannier function, as I call them, the Lego bricks of electronic structure. And this was due from our desire to do molecular electronics, to do electronic structure and transport properties in, say, a lead conductor lead formulation. In particular, we were working at the time with carbon nanotubes. Of course, again, close by in Rice, there was a huge effort on carbon nanotubes. We wanted to work on functionalized carbon nanotubes. You see, these are simple covalent aryl functionalization of nanotubes, but you see the difference. This nanotube electronic structure in the Bloch representation is very messy. In a Wannier representation, away from the functionalization, it looks like the electronic structure of a perfect nanotube, and then close to the functionalization is, functional group specific. And so, we build, maybe I won't go into detail, again, the capabilities. This is what Su-Chen Zhang used much later to do the topological surface states, but we build the capabilities to, say, calculate Green's functions, to calculate the transmission function in the ballistic regime for these carbon nanotubes. But in particular, what we realized very early on is that Wannier functions were very accurate interpolators. So they were really building, if you want, a tight binding model that was minimal. You could, have the least possible number of states that you could have to describe a manifold of bands, but they were also exact because they were an inverse mapping. So in the carbon nanotube, we decided that we wanted to describe, say, the valence states, the bonding combination of sp2 orbitals that give rise to the backbone, these covalent bonds, and the pz orbital. It would be the same in graphene. So if you think at graphene, you would have 2 atoms per unit cell. And so this minimal tight binding model would have per unit cell 3 covalent bonds, blue, blue, blue. In a carbon nanotube, there is curvature, so they are slightly different. But there are 3 covalent bonds for the backbone and 1 pz orbital on every state. So with 5 states on every unit cell, you could these Wannier functions, you could then calculate back from Bloch sums the Bloch orbitals at every k points n and k, and you could get back the band structure by, as usual, diagonalizing the Hamiltonian between the states. But because these Bloch states are written as a sum of Wannier functions that are localized, in this infinite sum, you can actually truncate away most everything. This is the same thing that happens in linear scaling. And so it becomes numerically very easy to just diagonalize this very small Hamiltonian matrix. And it works beautifully. This is why, I say it's an exact tight binding. With these 5 Wannier functions, in this case, we have 2 carbon nanotubes, the armchair and the zigzag. You see how perfectly we represent with these black lines the electronic structure around the Fermi energy. The dots is what you would get from, say, PWSCF, Quantum Espresso, Abinit, Siesta, and so on. So everything is reproduced basically perfectly in this case. Apart, of course, we have only 5 states for unit cells, so we have a finite number of states, and we are not getting any of this either antibonding dispersion or free electron band dispersions. And the beauty, maybe this is a bit complicated, but I just wanted to show you very quickly. We did it, say, for, in this case, carbon nanotubes. Let's for a moment take what is called a 5-5 carbon nanotube. So that's a unit cell of 20 atoms. So it's this sort of, ring of hexagons. And then it's periodic in this direction, say, parallel to the floor. And the Brillouin zone is this yellow Brillouin zone. In here, you do your plane wave calculations, and you get these red bands. Instead, what we were doing in this system was actually, because we wanted to functionalize it, that was the reason, we were not going to do, say, a primitive cell calculation. We were going to do a supercell calculation. So rather than 20 atoms, we were using 100 atoms, but gamma sampling only. So if you go from 5 atoms to if you go from 20 atoms to 100 atoms, your Brillouin zone becomes 5 times smaller. Is this darker yellow here? And that's the important point. We were only sampling it at gamma. So the only states that we knew about were the states at gamma, where you see this is a metallic nanotube, but at gamma it has a gap of 2 electron volts. And from these states in this blue rectangle, with the disentanglement procedure, we were able to build the optimal basis. And then from the optimal basis, using this idea here, from this omega n, we were building the psi Wannier functions. We were diagonalizing it, and we would get, you see, these black lines here. And these black lines are perfectly reproducing the red dots folded into our supercell. And they were giving us a metal, even if we started from something that had a 2 electron volt gap. And if we were building out of this localized state the Green's function with the recursive methods, and then calculating the conductance and density of states, you see, we were getting, remarkable results, not only say for, the fact that this system is a metal, but in particular, look at these Van Hove singularities that were coming out perfect from our Wannier tight binding model, even if the top of the band was exactly at a place that had nothing to do with the gamma point that we started with. So not only, say, outstanding interpolators and building blocks of the electronic structure, but you didn't even have to construct this Wannier function from an infinite solid. You could take a fragment, a carbon nanotube snipped and saturated with hydrogens. You could construct your localized orbitals. Then you take the ones in the center that are far away from the edge, and so they look bulk-like. And those with those orbitals that are bulk-like, you again construct the perfect structure of the infinite solid. So in this sense, these Wannier functions, this red, blue, and purple Wannier function, are the building blocks of electronic structure. So we use them not only to do ballistic transport. At a certain point, we also launched ourselves to doing a full, say, and this is maybe relevant for the school, sort of Green's function formulation for having electron-phonons, or in this case, electron vibration interaction inside the self-energies, and then calculating, say, inelastic quantum transport, finding out very interesting things about backflow and loop currents. These were just nanotubes that were sort of, starting to break apart and so on. In 3 minutes, I'll do the last 2 topics, so I'll accelerate. So just wake up in case I have sort of, gone hypnotized by Wannier function. So these are 2 very recent things that I'm very happy about. One is this issue of disentanglement, and if you want automated Wannierization, that has been a bit painful for 27 years or something. And we finally sit down with Zhongfeng Chao, PhD student, and Giovanni Pizzi, and we came out with a very simple idea, if you want. That is, you can take any band structure of a system, and what we are doing here is we are projecting onto the atomic orbitals. We take the atomic orbitals on the pseudopotential, but you could just build them up by yourself. And so the states that are colored, they have large projectability on atomic orbitals, and the states that are black and thin, I have very low projectability. And so what we did was change the criterion of selection of states to put into a disentanglement algorithm. Remember, before we said that we choose an energy window, and that is a very brutal way of choosing states to drop outside what we call the outer window, states to freeze, to keep as they are, that we call the inner window, and state to mix up. That's the critical thing with this optimal smoothness algorithm. So the only concept that you need to remember from this is that rather than having an energy window to keep, freeze, or drop states, we have a projectability threshold to freeze a state, to keep and throw them in the smoothness algorithm, or to drop them altogether. So you see that gives us, in something like the conduction band of graphene, the possibility of throwing away very low energy states just above the Fermi energy that we couldn't care less about because they have very low projectability onto atomic localized states, but instead a grasp state above here that are very localized, and that would be useful. So basically here we have a projectability threshold, we keep what is colored and we mix that around, and on that we do the optimal smoothness. It's very easy to choose universal threshold, but it's also very easy to do a systematic exploration of the thresholds, and the code also does that automatically. And the net result is that now basically we can Wannierize everything in an atom-centered basis. And so Jianfeng, you see, is on a run. He has already calculated 1.2 million Wannier functions, and by tomorrow probably 1.3 million, and this keeps going. So we are selling out actually Wannier function as if they were panini caldi, that I don't remember how you say it in English, and it looks all very good. So let me sort of overshoot my talk by 2 minutes, and I'll tell you the last things because it's really the dearest to me. And it's again, we have been working on this, I'm afraid, since 2007, but very happily so. This was a project that started with Ismail Dabo when he was a student of mine at MIT, has been gone on son, but the project is finally finished, and the code will be released with the next release of Quantum Espresso. Paolo will tell us, but it's probably just a matter of weeks. And this idea that I think is actually very powerful, and is an idea where exactly as density functional theory is a functional theory of a total energy as a function of what I call a static object and local, that is the charge density, is local rho of R, and is static, it doesn't depend on energy. What we have built is a functional theory for spectra that is doing what, say, GW aims to do, many body perturbation theory, that is getting spectral properties, getting charged excitation, but with a functional. You can't do it with a static functional, so you need to do it with a functional that is not only, say, local, and locality is very important, but it needs to be dynamical. That functional needs to be a functional of an object that is frequency dependent. But the very nice thing is that you can do it with an object that is, say, energy dependent in a quasi-particle spirit. So it doesn't depend on frequency arbitrarily, but is just different at different orbital energies. How do we got from here? We got, starting from this sort of obsession of mine with self-interaction, that is the thought that this expectation value should not depend on the occupation of the orbital. This is photoemission. What we are saying is we remove an electron from an orbital, and we look at the expectation value of this object. If the theory is self-interaction free, this is a heuristic definition, but this object, this expectation value, should not depend on the occupation of the electron itself. So if we wanted to enforce that I thought was a very good idea, that's what we wanted. If you were to do this in standard DFT, LDA with a carbon atom, you extract a 2s electron, this epsilon I will change by 10 electron volts as you go from occupation 0 to occupation 1. So the changes are huge in our standard functional. So what we said, we want to hammer out this dependency on the occupation. And to hammer out the dependency of occupation, what we did is that we take our base functional and orbital by orbital, you see this sum over I, we remove the term that we don't like. We remove what is the change in the energy with respect to occupation, say for a fractional occupation Fi between 0 and 1. So we hammer that out, and instead we add a green term that is linear in occupation. So it's proportional to the occupation with a proportionality constant eta I. And what is the eta I is nothing else than the energy at full occupation and the energy at 0 occupation, here written in an integral form. So this is all what you need to remember. So we have taken the DFT functional, and orbital by orbital, we have hammered out a self-interaction. We have made this expectation value constant, and there is nothing empirical in here. Okay, this is all well defined, with the only sort of additional term to keep in mind that this linearization would work if the orbitals were frozen. But if instead, as you extract the orbital, all the electrons in the system respond, you need to take into account screening. It's a bit like W, but this is really just, in our formulation, a scalar. It's an evaluation of the screening with respect to this process that is written in the orbital dependent basis. I won't tell you much more, but maybe an important step is that this functional give rise at the minimum to variational localized orbitals. And that's very important to get the right, say, thermodynamic limit when you go from a finite system to an infinite system. And I'll just leave you with the results. The very nice thing is that this Koopman's functional do really an excellent job in describing the band structure, not only, say, compared to density functional theory, that is not the right theory, or compared to hybrid functional that maybe for other reason they do some of this linearization. But when we start comparing it not only with GW, say G0W0, but with GW0 with self-consistent GW with vertex correction, they start to be seriously good. They are always much better than the G0W0. They are typically as good as self-consistent GW with vertex correction, but they are much better actually than all the GW approaches in representing the position of the bands with respect to the vacuum level. So I'm very optimistic. This is also, very useful materials for some of the photovoltaic, sorry, not photovoltaic, but say photocatalysis application. I think we finally have, say, a functional theory of spectral properties that is going to be publicly available very, very soon, and also in a very user-friendly manner. So I conclude acknowledgements. I mean, this started when I was a postdoc with David Vanderbilt. Ivo Sousa joined quickly in. I moved to MIT, Ivo moved to Berkeley, Arash Mostofi and Jonathan Yates came over. We built the Wannier 90, Fortran 90 sort of evolution of the code. Giovanni Pizzi came at EPFL, he has been a driving force. Antimo Marrazzo, that is here, you'll see us now sort of really taking leadership in there. So this is really an acknowledgement to the people, mostly at MIT, that did some of the early work, and the people at EPFL that did the Koopman's work that I just described. If you want to know more, you'll have a lot of tutorials. These maybe are the two references, the code, the review of modern physics, the latest, something I'm very proud that the code you see becoming not anymore driven originally by me, then by Arash and Jonathan, then by Giovanni Antimo, but really becoming a community code with, say, a community model of development. And this ensures that, a code, maybe Abinit has been a very, very good example of how to transform, say, a code into a community code, making sure that it lives on. And then I conclude with this slide that has nothing to do, but I thought that this is a school, and maybe there are a number of people that are new to this world of electronic structure. So this has nothing to do with Wannier function, but last year we put a lot of effort to write a bit of panorama of the entire world of electronic structure simulation. With this, I'll shut up and thank you a lot for your attention.
Thank you, Professor Marzari, for a very nice talk. I have a very quick question that is, in the last part of your presentation, you talk about the parameter, not parameter, the alphas for the screening. I'm just wondering how that is being determined.
Yeah. So this is, for those of you that are familiar with DFT plus U in the formulation of Matteo Cuccoccioni and Stefano De Gironcoli. So if you remember, that is just a second derivative, is a response property of the system. So originally we used to calculate with finite differences. So we would do, say, if it was a solid, a supercell, and we would actually fill up or empty the orbital and finding, you know, the sort of number that would give us the linearization. Then Yuri Timrov has been involved in a very comprehensive rewriting of what is there in density functional perturbation theory, both for the Hubbard parameters, for the Hubbard U and the Hubbard V, not only say as a linear response property, but using all the mechanism of density functional perturbation theory. So not doing a calculation in supercells, but doing a calculation in the primitive cell and sampling a monochromatic perturbation at different wavelength. And Nicola Colonna has just now finished the same thing to calculate the alpha. So basically the alpha is calculated from a second derivative for the case in which the perturbation is screened or unscreened. So there is a dielectric matrix in front. So in that sense, this is a W. And thanks to density functional perturbation theory, this calculation can be done in a primitive cell. So now it's all very automated. And there are actually in the release, there is also a Koopmans functional.org website, Koopmans-functional. We tried to buy the Koopmans.org, but they told us that they wanted $5,000. So, you know, I said, guys, you know, we all cut our salaries by 1,000. They refused, so we find 5,000 elsewhere. We went back and they said, here are the $5,000. And they said, well, now we want $50,000. And so if you guys can put together, you know, the 45 missing, we can have the Koopmans website. Right now, there is the Koopmans-functional. By the way, for those of you that don't know Koopmans, Koopmans did his master degree with Ehrenfest, I think. And then he got fed up and he went into economics and won the Nobel Prize in economics. But that's a detour. Anyhow, it's all linear response theory, basically, screened and unscreened. And this is written actually in the different papers by Nicola Colonna. So it's all published.
Okay. Question?
Next week, so just hours. Okay, so follow the New York Times, and when it flashes, you're ready to go. Thanks to Paolo also for the infinite work that he puts in this.
Yeah, thanks for the talk. You mentioned that we can obtain the Unitary transformation to the projection to the 3 times the local orbitals. I was asking, how do you actually select the orbitals, and is the selection doesn't matter for the minimization of the situation?
Yeah, so that's you know, so a posteriori it's sort of easy to do. I mean, you know, let's take silicon. Okay, so what would I choose? You know, because I know I want to get 4 covalent bonds, I would choose things like a Gaussian centered on the mid bond. Okay, that is a very intuitive strategy. So if you know what you want and you understand the band structure and you understand the bonding of the material, you can do a very good job. So I take silicon, I put, you know, just spherical Gaussians at the center of every covalent bond, and I do this projection, I unitarize them with a load in a sort of orthogonalization, and then I get certain phi that will look very good. If I change the width of the Gaussian, the phi and k will change, but very, very little, okay, because I've sort of done the right thing. But maybe if instead, if I put rather than a Gaussian something different, I might get a different result. If I wanted, say, to get the antibonding orbitals, so I was mixing stuff over there, and if I put a Gaussian on the center of the bond, I would do a very bad job because I want to get the antibonding orbitals that have the plane mirror symmetry. So it requires a bit of intuition. Of course, you know, if you want to get tight binding models, you know, getting for each atom the S, the P, the D, and the, you know, sort of getting this could actually work very well. But in some ways, that's what the projectability now does for you.
Yeah, we have time for one last question. So I have a question about the functions that you showed again. So if you mentioned they are called different functions, I'm just wondering if they still they are valid for the so-called DFT theorem or the ionization potential.
Yeah, so the idea here is that not only you want to have exact DFT by construction gives you the exact ionization potential because exact DFT gives you the exact charge density. You take a molecule, the asymptotic decay of the charge density is determined by the Kohn-Sham HOMO. So to have the exact charge density, you should have the exact Kohn-Sham HOMO, but everything else you don't have. And in particular, you don't have the LUMO, but say you don't have anything. And that's the limitation of a static potential. So it's the same potential that acts on every state. So the famous derivative discontinuity, that is, you know, you should think, you know, it's just mad that you have a theory where you have, you know, a molecule that is falling on a surface, and, you know, as soon as the LUMO get occupied, the LUMO becomes the HOMO, and now it has to be exact. So the exchange correlation needs to do a jump out of nowhere. So if you want, for spectral properties, a static potential doesn't mean anything. In many-body perturbation theory, you have a potential that is non-local and dynamical. And you have, you know, a diagrammatic sort of map, not the map, you have a diagrammatic path to construct, you know, your approximation. What I'm saying is that let's instead build a functional. So let's build, say, a self-energy, or let's build a spectral potential through a functional. Now, building non-local things is hopeless. You know, this is the same great failure, if you want, of reduced second-order density matrix. You know, we have the functional of the energy as a function of the reduced second-order density matrices. So, but we don't have the representability. Anything that you build a function of RR prime twice is not going to make any sense. And my argument is that we can build something that is local and dynamic. So you need the dynamic part. You could trade it off for non-locality, but it's a mess. You need it dynamical, then you don't have a derivative discontinuity. Every spectral potential or every Koopman's potential acts differently on every orbital, and it does for each orbital the right thing. And you know, every time, so we haven't even worked, so we don't have a representability proof. But exactly as you know, every charge density that you use is good, I think everything local but dynamical, there are things about, say, time ordering that are a little bit more tricky, but in general, everything that we have built seems to work very well. That is, you know, completely the opposite experience with reduced second-order density matrix, where everything that you build, if you don't put a lot of thought, doesn't make any sense. But it's work for the future.
Okay, thank you.